N-type germanium crystal and an indium pellet are alloyed together to produce a PN junction. This process is then repeated on the other side of the crystal to form a further PN junction. In this way, a crystal comprising three regions is formed: an N region sandwiched between two P regions. At this stage, the concentrations of majority and minority carriers are represented by horizontal lines. If a forward voltage is now applied to the left-hand junction, the minority concentrations in the vicinity of this barrier will increase. If, in addition, a reverse voltage is applied to the right-hand junction, the minority concentrations in the vicinity of this other barrier will decrease. The behavior of this PNP crystal can be explained by simply considering the minority concentrations. So that we may see more clearly the actual values of these concentrations, the logarithmic scales of the vertical axes are now substituted by linear ones. The hole concentration in the central N region is rather high near the left-hand junction due to the diffusion of holes from the P region. As the electrons are the majority carriers, the holes will readily recombine, causing a sharp fall in the concentration curve. Very few holes penetrate further into the N region, with the effect that here the hole concentration remains at its equilibrium level. Because of the reverse bias applied to the right-hand junction, the hole concentration near this junction is below its equilibrium level. If we consider the currents flowing in the circuits corresponding to the two junctions, it will be seen that a large forward current flows in the left-hand circuit and a very weak reverse current in the right-hand circuit. These currents are directly related to the concentration levels just explained. In explaining these levels, it was shown that a great number of holes diffuse from the left-hand P region into the central N region, but that hardly any pass through it. This is due to the comparatively large width of this N region. However, if we considerably decrease the width of this central region, more and more of the holes emitted by the left-hand P region will be absorbed by the right-hand P region, and the currents flowing in the two circuits will become very nearly equal. A closer examination of this central region will reveal that the holes move at random in it. Therefore, the flow of holes across this region is a diffusion of holes, caused by the difference in concentration between left and right. By dividing the central region into a number of equal zones, it can be seen how the average hole concentration decreases from left to right. This decrease is, in fact, linear, and can be expressed as a straight line drawn at an angle to the horizontal axis. The value of the current flowing in the right-hand circuit is a function of this angle. The currents flowing in the crystal are also related to the concentrations of the minority electrons in the P regions. Close to the junctions, the concentrations deviate from the equilibrium level, but the small deviation at the right-hand junction can, for the moment, be neglected. The steep curve representing the appreciable deviation at the left-hand junction can be replaced by a straight line, and the angle that this line forms with the horizontal axis has a direct relationship with the number of electrons diffusing from the central region into this P region, where they recombine with the majority holes. To ensure a continuation of this electron flow, the battery has to supply electrons to the central region. This PNP crystal, due to its very narrow central region, constitutes a transistor. The three regions are, from left to right, the emitter, base, and collector, and the currents flowing in the circuits are known as the emitter current, IE, base current, IB, and collector current, IC. The emitter current is the sum of the collector and base currents. Therefore, when the base current is very small, the collector current and the emitter current will be almost equal. This condition must be fulfilled when transistors having a high amplification factor are required. A small base current is indicated by a small angle in this electron concentration curve, and the way in which a small angle is obtained will now be analyzed. So far, we have only considered a PNP crystal, whose three regions contain equal impurity concentrations, shown here on a logarithmic scale. If we now consider a crystal in which the number of foreign atoms in the base is reduced, then the electron concentration in the base region will also be reduced, and consequently, the hole concentration increased. This means that the hole concentration in the base is considerably higher than the electron concentrations in the emitter and collector regions. As we are again considering only minority concentrations, we will return to a linear scale. The emitter-base junction is again biased in the forward direction. Consequently, the minority concentration near this junction increase. That is to say, the electron concentration in the emitter and the hole concentration in the base. The collector-base junction is biased in the reverse direction, which means that the hole concentration in the base decreases near this junction. If we now study the concentration graphs, we will see that the angle formed by the hole concentration curve with the horizontal axis is large. This means that an appreciable collector current is flowing. On the other hand, the angle formed by the electron concentration curve in the emitter is small, and therefore the base current, which may be expected, is also small. However, if we measure this current, it will be seen that the meter indicates a slightly higher value. The reason is that some of the holes diffusing from the emitter into the base will not be absorbed by the collector, but instead will recombine at the surface of the crystal, and thus cause an increase in the base current. This effect can be largely avoided by increasing the surface area of the collector-base junction. In the transistor configuration shown, the emitter-base junction forms part of the input circuit, and the collector-base junction part of the output circuit. The base region is then common to both input and output circuits, hence the name common base configuration. As the emitter and collector currents are, respectively, the input and output currents, it is their ratio which is referred to as the current gain in common base configuration. If we now disconnect the input circuit, a weak current will flow in the output circuit, caused by the reverse voltage applied to the collector-base junction. This residual current is referred to as -I CB0. In this new configuration, the input circuit contains the emitter-base junction. And the output circuit, both emitter-base and collector-base junctions. Thus, the emitter is common to both the input and output circuits, hence the name common emitter configuration. As the base and collector currents are, respectively, the input and output currents, it is their ratio which is referred to as the current gain in common emitter configuration. By disconnecting the input circuit of this common emitter configuration, a rather large residual current will be seen to flow in the output circuit. This current can be explained by first considering what happens when no external voltage is applied. In this condition, the two barriers are identical in width. However, if the voltage is again applied, the reverse bias of the base collector junction will cause holes to flow into the collector and electrons to flow into the base. Because the base becomes slightly negative with respect to the emitter, the base emitter junction will be forward biased and the barrier width will decrease. This enables an appreciable number of holes to diffuse into the base and flow on to the collector. The currents now flowing are a weak electron current from collector to base, and a much stronger hole current from emitter to collector. Together, these currents make up the residual current, but as the electron current is so weak, it can be neglected. Thus, the hole current alone can be said to determine the residual current. In common emitter configuration, this current is called -I CE0. A third configuration is obtained by making the collector common to both input and output circuits. In this case, the emitter current is the output current and the base current the input current. Their ratio is known as the current gain of the transistor in common collector configuration. By again disconnecting the input circuit, a large residual current will be seen to flow in the output circuit. This current is called IEC0.